Caesar the Circulate talking about tangent lines. And I am a tangent, I guess you could say.
First vocabulary term is tangent to a circle. That would be a line in the plane of the circle that intersects the circle at exactly one point. So take a look at our example down here. We have circle G and we have line AB or BA. Now notice, line AB or BA intersects circle G at exactly one point, point P. Therefore, we can say that line AB or BA is tangent to circle G at point P. Next thing we're going to talk about is the point of tangency. That would be the point where the circle and the tangent line intersect. So here we have the same example with circle G and line AB or BA. And now that line is intersecting circle G at exactly one point, point P. That line AB is tangent to circle G. We also know that because point P is the only point where line AB intersects circle G, point P would be considered the point of tangency. Let's talk about inscribed in. So a circle is inscribed in a polygon if the sides of the polygon are tangent to the circle, whereas a polygon is inscribed in a circle if the vertices of the polygon are on the circle. So let's take a look at this first scenario. A circle, like circle G, is inscribed in a polygon, like triangle XYZ, if the sides of the polygon are tangent to the circle. And you see that each of the sides of the polygon are tangent to the circle because they only intersect the circle at exactly one point, meaning point A, point B, and point C would be considered points of tangency. Now the second part of this says a polygon is inscribed in a circle, so a polygon here would be triangle ABC. It's inscribed in a circle, circle P, if the vertices of the polygon, points A, B, and C, are on the circle. And you see that each of those points lie on the circle. Therefore, this polygon, triangle ABC, is inscribed in circle P. Now, circumscribed about is kind of the opposite of inscribed in. So a circle is circumscribed about a polygon if the vertices of the polygon are on the circle. A polygon is circumscribed about a circle if all the sides of the polygon are tangent to the circle. So let's show you how this works with our example down here. So a circle, circle P, is circumscribed about a polygon, triangle ABC, if the vertices of the polygon are on the circle. And you see that points A, B, and C lie on circle P. Therefore, circle P is circumscribed about triangle ABC. The second part says a polygon, here we have triangle XYZ, is circumscribed about a circle, circle G, if all the sides of the polygon are tangent to the circle. And we see that each of these sides are tangent to circle G at exactly one point. Here, this side, segment XY, is tangent to circle G at point A. Here, this side, segment XY, is tangent to circle G at point B. Here, this side, segment XZ, is tangent to circle G at point C. Therefore, triangle XYZ is circumscribed about circle G.
I really hate that Woody Harrelson. Example time. Woo-hoo-hoo-hoo.
Now example 1 says copy each figure and draw the common tangents. If no tangent exists, state no common tangent. So in each of these examples, you're going to be given two circles and you're going to be asked to draw common tangent lines, meaning a line that is tangent to both circles. So in this first example over here, we have this large circle and we have a smaller circle. So is there a line or lines that we can draw that would be tangent to both circles? Well, yeah, I could draw a line intersecting this big circle right here and then continuing on to intersect this little circle right here. Therefore, this line would be a common tangent to both circles. We could also do the same thing from the other direction. We could draw a tangent line touching this circle at exactly one point right here and then continuing on to intersect the other circle at exactly one point. Therefore, these two lines would be considered the common tangents of these circles. Part B, doing the same thing. We are again given two circles and we are tasked with drawing common tangents, meaning a tangent line that intersects both circles at exactly one point. So let's start with a line coming in from this side that would intersect this big circle at exactly one point and then continue on to intersect the little circle at exactly one point as well. This would be a common tangent of both circles. Same thing over here. We have another common tangent line that would intersect the big circle at exactly one point and then continuing on to intersect the little circle at one point. And then assuming that each of these circles intersect at exactly one point right here, we could also draw a line passing through that one point, making this a common tangent as well.
Banana's good, humans bad. You try.
So part 8, we're tasked with doing the same thing, except this time we have concentric circles. We have a circle within a circle. So how does this work? How can we draw a line that is tangent to both circles at exactly one point? The answer is you can't. There is no line that you could draw that would be tangent to this circle inside that would only intersect the outer circle at one point. It would have to intersect the outer circle at 2 points. Therefore, these two circles have no common tangent lines. Part B, doing the same thing, we're looking for common tangents between these two circles. So, is there a line or lines that we can draw that would be tangent to both circles at exactly one point? Yeah, there are several here actually. So if I were to draw a line intersecting the big circle at this point right here, and then continuing on to intersect this little circle at exactly one point right there, that would be considered a common tangent. Same thing from the other direction. If I were to draw a line that would intersect the big circle at exactly one point right here, then continuing on to intersect the little circle at exactly one point right here, that would be considered a common tangent. We also have the ones on the outside. So if I were to draw a line coming here, intersecting our big circle at exactly one point, continuing on to intersect our little circle at one point, that would be a common tangent. And then same thing from the other side. If I were to draw a line intersecting our big circle at this point and continuing on to intersect our little circle at this one point right here, that would also be considered a common tangent. Now let's talk about some tangent line theorems. So the first one says, if a line is tangent to a circle, then the line is perpendicular to the radius drawn to the point of tangency. So this is pretty straightforward. Let me show you how this works with our example down here. So this says, if a line is tangent to a circle, so down here we have line AB or BA, that is tangent to circle G because it only intersects it at one point, point P. Because of this, the line is perpendicular to the radius drawn to the point of tangency. So if I were to draw a radius going from the center of the circle, point G, to that point of tangency, point P, that segment right there, that radius, would be perpendicular to our tangent line. That's what this theorem is saying. The second tangent line theorem says if a line in the plane of a circle is perpendicular to a radius at its endpoints on the circle, then the line is tangent to the circle. So this is basically the converse of the theorem we just talked about. Looking at our example, this says if a line AB or BA, in the plane of a circle, circle G, is perpendicular to a radius at its endpoint on the circle. So if line AB is perpendicular to this radius right here, segment GP, which we see that it is, at point P, then we know that this line AB, would be tangent to circle G. So because this line is perpendicular to this radius at this point P on the circle, then we know that line AB must be tangent to circle G at point P. Now the third tangent line theorem says the two segments tangent to a circle from a point outside the circle are congruent. So let's explain this. Looking at our example down here, we have two segments, segment AB and segment CB, and they are tangent to circle G down here. And you can see that segment AB is tangent to circle G at point A. Segment CB is tangent to circle G at point C. Because they are both tangent to circle G and they intersect at the exact same point out here, point B, these two segments then must be congruent to one another by this theorem. Now example 2 says segment ML and segment MN are tangent to circle G. Find the measure of angle LMN. So to start this example, what we need to do is set up an equation to solve for the measure of angle LMN. Well, you can see here that we have actually a quadrilateral LMNG. Because it's a quadrilateral, we know that the sum of the measures of the interior angles here has to equal 360 degrees. So all we have to do is add up the measure of each of these angles, set it equal to 360, and then we can solve for the measure of angle LMN. The only problem is we only have one angle. We're not given either of these angles right here. Well, we do know that segment ML and segment MN are tangent to circle G. We also know that segment GL and segment GN would be radii of circle G. And we also just saw a theorem that says if a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. So we know that segment GN and segment MN would be perpendicular. Same thing up here. Segment ML and segment GL would be perpendicular. Because of that, we know each of their measures must be 90 degrees. So in this equation over here, we can substitute 90 degrees in for each of those angle measures, and we can substitute 117.9 degrees in for the measure of angle NGL over here. So when we do that, the only unknown angle measure would be the measure of angle LMN, which we can solve for. So let's combine like terms. 90 plus 117.9 gives you 297.9. We subtract that from both sides, we get the measure of angle LMN is 62.1 degrees.
Time for you to try, or I'll be a monkey's uncle.
Okay, so this time it says segment BC is tangent to circle G. Find the measure of angle CAG. Round answer to the nearest hundredth. So down here, not only do we have circle G, but we also have this triangle ABC. Now within this triangle right here, we're trying to find the measure of angle CAG, which would be this angle right here. So in order to find that angle measure, we clearly need to find x. And to find x, we have to set up an equation in order to solve for x. And because we have a triangle here, what we can do is we can add up the measures of the interior angles of this triangle and set it equal to 180 degrees by the triangle angle sum theorem. So now all we have to do is plug in what we know. We know the measure of angle BCA is 11x plus 8. That goes in here. We know the measure of angle CAG, which is what we're trying to find, is 16x minus 7. So that goes in here. The only question is, what is the measure of angle GBC right here? Well, we know that segment BC is tangent to circle G at point B. We also know that if a line is tangent to a circle, then it's perpendicular to the radius drawn to the point of tangency, meaning this segment right here, this radius, segment GB, would be perpendicular to our tangent line right here. Because of that, we know its measure must be 90 degrees, so we can plug that in here. Now all we have to do is combine like terms, so 90 plus 8 minus 7 is going to give you 91, and then 11x plus 16x is going to give you 27x. We then solve for x by subtracting 91 from both sides, dividing both sides by 27, we get x is equal to 89 over 27. Now we're going to leave it like this. We don't want to round too early, otherwise we'll get the wrong answer. So we leave it in exact form so we can find the exact measure of angle CAG. So the measure of angle CAG we said was 16x minus 7. So I'm going to take what we found x to be, 89 over 27, plug it in for x right here, simplify, and we end up getting that the measure of angle CAG is approximately equal to 45.74 degrees when we round to the nearest hundredth, which is 2 decimal places. Now example 3 says determine whether a tangent line is shown in the diagram. So in this figure we have circle G and we have triangle ABC, and it wants us to determine whether a tangent line is shown in the diagram. Well, there's only 3 line segments here: segment AC, segment BC, and segment AB. And you see that segment AC intersects circle G at 2 points. Therefore, it cannot be a tangent line. Segment AB is a diameter of circle G. Therefore, it cannot be a tangent line. So it's really just referring to segment BC over here. Now, is there a way to show that segment BC is tangent to circle G at point B? Well, there was a theorem that says if a line in the plane of a circle is perpendicular to a radius of the circle at its endpoint, then the line is tangent to the circle. So if we can show that segment BC right here is perpendicular to this radius, segment GB or BG, then we could say that segment BC is tangent to circle G. So all we got to do is show that this is a 90-degree angle, or a right angle, meaning we need to show that this triangle right here, triangle ABC, is a right triangle. So how do we show that triangle ABC is a right triangle? Well, we use the Pythagorean theorem. A squared plus B squared is equal to C squared. If A squared plus B squared does in fact equal C squared for this triangle, triangle ABC, then we know it's a right triangle, meaning that segment BC would be perpendicular to segment BG, meaning that segment BC would be tangent to circle G at point B. So let's go ahead and plug in what we know. We know that the only one that matters is your C value. Your C value has to be the side length opposite the 90-degree angle. Now in this case, we're hoping angle B right here is going to be our 90-degree angle. Therefore, the measure of the side opposite, the measure of segment AC, is going to be what we plug in for C over here. That means that the measure of segment AB and the measure of segment BC, we can plug in for A or B over here. It doesn't matter. Well, we know the measure of segment BC, that's 15 feet. But what about the measure of segment AB? Well, we're only given half of that. Well, because this is a diameter, and this measurement right here, the measure of segment AG or GA, is half of our diameter, it's a radius, then we know that the other measurement over here, the measure of segment BG or GB, would have to be 2.5 feet as well. So we're going to take the measure of segment AB or BA, which is 5 feet, plug that in for A. We're going to take the measure of segment BC or CB, which is 15 feet, plug it in for B. And we're going to take the measure of segment AC or CA, which is 16 feet, and plug it in for C. Now all we have to do is square each of those, add these together, and we see that 250 does not equal 256, meaning A squared plus B squared did not equal C squared, meaning that this is not a right triangle, meaning that segment BC is not perpendicular to segment BG, meaning that segment BC is not tangent to circle G at point B. Therefore, we can say that no tangent lines appear in our figure over here.
Yes, sir.
Okay, doing the same thing. We are again given a circle, circle G, and we are given a triangle, triangle GEF. And we are tasked with determining whether a tangent line is shown in the diagram. Well, we only have 3 line segments here. And this line segment, segment GF, clearly, if it were to continue, would intersect circle G at more than one point. Segment GE over here is a radius of circle G, so that can't be tangent to circle G, meaning that the only line that we're concerned with would be this line segment right here, segment EF. Now, we've already talked about a theorem that says if a line in the plane of a circle is perpendicular to a radius of the circle at its endpoint, then the line must be tangent to the circle. So we need to show that segment GE is perpendicular to segment EF. Now, the way we do that is by determining if triangle GEF is a right triangle, meaning this would be a 90-degree angle. And the way we prove a triangle is a right triangle is by using the Pythagorean theorem. We need to figure out, does a squared plus b squared equal c squared? Now, remember, the only variable over here that it matters what we plug into would be our c value. The c has to be the side length opposite our 90-degree angle. And in this case, we're hoping angle E right here is going to be our 90-degree angle. So the measure of segment GF is going to be what we plug in for c over here. But the issue is we're missing a part of segment GF. We don't have this segment right here. Well, we do know that segment GE is 4 inches, and we know that's a radius of circle G. We also know that this segment right here would also be a radius of circle G, meaning that this segment right here, its measure would also be 4 inches. So the measure of segment GF then would be 8 inches plus 4 inches, which is 12 inches. That's what we're going to plug in for C over here. The measure of segment GE and the measure of segment EF can go in for A or B. It doesn't matter. I'm going to plug in the measure of segment GE, 4 inches for our A, and then plug in the measure of segment EF, 8 rad 2 inches for our B. Now all I have to do is square each of these, then add these two together and see, does A squared plus B squared equal C squared? Yes, it does, meaning that this is in fact a right triangle, meaning that this line right here is perpendicular to a radius at its endpoint on the circle, meaning that this segment right here, segment EF, would be tangent to circle G at point E. Now example 4 says find the measure of segment BG. Assume that segments that appear to be tangent are tangent. Leave your answer in simplest radical form if necessary. So we again are given a circle, circle G, and we are given a triangle, triangle GBC, and we are tasked with determining the measure of segment BG right here. Well, the good news this time is it says assume that segments that appear to be tangent are tangent. So in this figure, the only segment that appears to be tangent would be segment BC. It is tangent to circle G at point B. Now because this segment right here is tangent to circle G at point B, that means, based on one of the theorems we talked about, it is going to be perpendicular to a radius drawn to that point of tangency. So we know that segment BC right here must be perpendicular to segment BG, making this triangle right here a right triangle. So now this problem has gone from super complicated to just finding the missing side length of a right triangle. So how do you find the missing side length of a right triangle? You use the Pythagorean theorem. A squared plus B squared is equal to C squared. Now the only variable over here where it matters what we plug in would be our C value. That has to be the side opposite our 90-degree angle, which in this case would be the measure of segment CG or GC. That means the measure of segment BC and the measure of segment BG we can plug in for A or B. It doesn't matter. I plugged in the measure of segment BG for A and the measure of segment BC for our B. Now all we have to do is plug in what we know. We know the measure of segment BC is 7 centimeters. That's going to go in here. We know the measure of segment CG is 11 centimeters. That's going to go in here. We then square each of those, solve for the measure of segment BG by subtracting 49 centimeters squared from both sides, square rooting both sides. Now because technically we're square rooting a variable squared over here, on the other side we need to put plus or minus. Now normally you would just plug this in your calculator, call it a day, but here it says to leave your answer in simplest radical form, meaning we need to simplify this radical. So we need to break up rad 72 into 2 radicals that multiply together to make rad 72. One of those numbers needs to be a perfect square though. So what perfect square goes into 72? That would be 36 and 2. So rad 36 times rad 2 gives you rad 72. We chose 36 because that's a perfect square. The square root of 36 is going to be 6, and then rad 2 just stays rad 2. Now, rather than writing plus or minus 6 rad 2, we look at our problem, and we're dealing with side lengths of triangles. We're dealing with geometric figures. Because of that, we are not going to have any negative side lengths. We can't have a negative radius. So instead, we're just going to take the positive version, the principal root, and we're going to say the measure of segment BG is going to be equal to 6 rad 2 centimeters.
Pretty soon, I'm going to see you at the zoo. You try it.
Okay, doing the same thing here, except this time it wants you to find the measure of segment GF. It also says to assume that segments that appear to be tangent are tangent. So we again are given a circle, circle G, and we're given a triangle, triangle GEF. Now, because we're assuming that segments that appear to be tangent are tangent, we look for our tangent segments down here. And the only one that appears to be tangent would be segment EF, because segment GE, if you were to continue that on, would clearly intersect the circle at 2 points. Segment GF, that's a radius of circle G, so that's not going to be tangent to our circle, meaning segment EF, that's the only one that's left. And we know a theorem that says if a segment is tangent to a circle, then it is perpendicular to the radius drawn to that point of tangency, meaning segment GF and segment EF are going to be perpendicular to one another, making this a right triangle. Meaning all we have to do to find segment GF over here, the missing side length of a right triangle, would be to use the Pythagorean theorem. A squared plus B squared is equal to C squared. Now remember, C is the only variable that it matters what you plug in for. It has to be the measure of the side opposite the 90-degree angle, which in this case would be the measure of segment GE. So that's going to go in for C. That means the measure of segment GF and the measure of segment EF, it doesn't matter which one you plug in for A or B. I'm just going to plug in the measure of segment GF for our A and the measure of segment EF for our B. Now we just plug in what we know. We know the measure of segment EF is 20 meters. That's going to go in here. The measure of segment GF, we could just leave the measure of segment GF and solve for it that way like we did last time. Or you could give it a variable if you want, like X. So we can plug in X here for the measure of segment GF. But what about the measure of segment EG? We're only given part of it. We have this segment out here is 12 meters. But what about this segment right here? Well, isn't this segment right here a radius of circle G? Meaning that it would be the exact same measure as the measure of segment GF. Meaning that if we're saying the measure of segment GF is X meters, then the measure of this segment would also have to be X meters. So for the measure of segment EG, I'm going to plug in X plus 12 meters. Now what I could do is I could square each of these. So X squared is just going to be X squared. 20 squared is going to be 400. And then X plus 12, the quantity squared, is the same thing as X plus 12 times X plus 12, meaning I have to FOIL this. And if you forgot how to FOIL, remember you multiply the first terms together, so X times X gives you X squared. Then you multiply the outer terms together. X times 12 gives you 12X. Then you multiply the inner terms together. 12 times X gives you 12X. Multiply the last terms together. 12 times 12 gives you 144. Add together those two middle terms. 12X plus 12X gives you 24X. Now we solve for X, but we have X squareds. Well, since there's just a 1X squared on this side and a 1X squared on this side, I can subtract 1X squared from each side and they actually cancel each other out. Now all I have to do to solve for X is just subtract 144 from both sides, divide both sides by 24, I get X is equal to 256 over 24. Now we look at the question. What did we just find? We found X, which was the measure of segment GF, which is exactly what we were trying to find. So we should be done, except how does this question want our answer? Well, it wants us to round the answer to the nearest thousand, which is 3 decimal places. So we're going to divide this in our calculator, round it to 3 decimal places, and we get that X, or the measure of segment GF, is approximately equal to 10.667 meters. Now example 5 says find X. Assume that segments that appear to be tangent are tangent. Round your answer to the nearest tenth if necessary. So we are again given a circle, circle G, and we're given 2 segments that are both tangent to circle G. Now we want to find X. So how do we find X? Well, we need to set up an equation in order to solve for X. So in this example over here, X appears in the measure of segment CB and in the measure of segment AB. So we need to figure out how are these 2 segments related. Well, both of these segments are tangent to circle G at points A and C respectively. We also see that these 2 segments are tangent to the circle from a point outside the circle. They both intersect at point B. Therefore, by that theorem, we know that 2 segments that are tangent to a circle from a point outside the circle must be congruent to each other. So we know segment AB must be congruent to segment CB, meaning that their measures must be equal to each other. So we can set the measure of segment AB, which is 3x plus 18, equal to the measure of segment CB, which is x squared. Now all we have to do is solve for X. Oh, but we have an X squared and an X. Well, we can't subtract those from one another. So what we're going to do when this happens is we're going to get everything to one side of the equation. I'm going to subtract 3X from both sides of the equation, and I'm going to subtract 18 from both sides of the equation. Now this should look somewhat familiar from your Algebra 1 days. I have a quadratic trinomial set equal to 0. So in order to solve this for X, there's a couple different ways I could do this. I could use the quadratic formula. I could use factor by grouping, or I could use a magic X in order to factor this, then use the 0 product property and solve for each of the x's. So what I'm going to do is I'm going to factor this, and if I were to factor using a magic x, what I would do is take my a value 1, multiply it to my c value, -18, put that on top of the magic x, then take my b value, -3, put that on the bottom. Now think about two numbers that multiply together to make -18 and add together to make -3. That would be -6 and +3. So when I factor this, it ends up becoming the quantity x minus 6 times the quantity x plus 3. We set that equal to 0. Now we have two things multiply together equals 0, meaning by the zero product property, either x minus 6 is equal to 0 or x plus 3 is equal to 0. We solve each of these. Over here we get x is equal to 6. Over here we get x is equal to -3. Now typically what happens in geometry is you get a negative number as one of your answers and you say, oh, can't be that one. But here, if I were to plug in -3 for x here and here, I would get positive side lengths. So I need to check to make sure that both of these actually work out. What I'm going to do, since I know that segment AB is congruent to segment CB and their measures are equal to one another, I can take those measurements, set them equal, and now I can plug in each of these x values to see if they actually do in fact equal one another. So I'm going to take 6, plug it in for x here and here. When I do that and simplify, I end up getting 36 is equal to 36, meaning if x were equal to 6, the measures of both of these segments would be equal to one another, so that is one of our answers. Now we need to do the same thing for the other x value that we found, -3. We're going to plug it in for x here and here. And when we do and simplify, we end up getting 9 is equal to 9, meaning that if x were equal to -3, both of the segment measures would be equal to one another. They would both equal 9. Therefore, -3 is also one of our answers. So we in fact have two answers to this question.
You guys know King Kong? He's my brother. You try.
Okay, this says below is the symbol representing the Deathly Hallows from Harry Potter. Find the perimeter of the triangle circumscribed about the circle. So in this question, we are trying to find the perimeter of this triangle, meaning we have a couple different segments that we need to find the measure of. So what we're going to do is we're going to use our knowledge of circumscribed about. What does that mean? Well, this triangle is circumscribed about circle G, meaning that each of these sides are tangent to the circle at each of these 3 points. Now what's going to help us solve this is one of the theorems we talked about earlier. We have 3 sets of segments that are tangent to the circle from a point outside the circle. Because of that, we know that each of these sets of segments are going to be congruent to each other. So let's determine which segments are congruent to each other. Because these two segments are tangent to circle G from a point outside the circle, they must be congruent to each other, meaning that if this segment over here is 8 centimeters, this segment over here must also be 8 centimeters. Same thing over here. We have two segments that are tangent to circle G from a point outside the circle. Therefore, these two segments must be congruent to each other. So if this segment is 8 centimeters, this segment must also be 8 centimeters. Same thing up here. We have two segments that are tangent to circle G from a point outside the circle. Therefore, those two segments must be congruent to each other. Therefore, their measures must be equal. So now, in order to answer this question, all we have to do to find the perimeter is just add together all of the segment measures for our given triangle. So if I were to add up all of these segment measures, I end up getting the perimeter of our triangle over here is going to be 44 centimeters.